Good morning. So we're going to be going over orbital stuff today. And so this is the beautifully drawn. I drew this picture of Earth myself. It's wonderful. But this is a satellite. And so a satellite we could just call, it could be like a space station. It could be like another planet. It could be anything that's orbiting. We're just using Earth and a satellite for an example. And so remember, an orbit follows uniform circular motion, right? And we know that this thing is being held in place. It can't go flying off, on a straight line into space, because as it's trying to go flying off, the Earth is actually pulling on it with a force of gravity. And that force of gravity is directed towards the center of the Earth. And that's all there is. It's also in space. So there's nothing else actually in contact with it. The only force that it has acting on it is a long-range force of gravity. And so you're going to get questions on the AP exam that ask you about things like orbital speed or orbital period, all right? And so we're going to break down how we approach these problems for those two setups. So this is part one of a two little video thing, and we're going to be talking about orbital speed. So if you see orbital speed or just speed v or anything like that, right? This is how we're going to approach it. I know the forces acting on this thing. So right away I'm like, okay, I'm going to set up Newton's second law because I know the forces. I'm wanting to know about the motion of this thing. So Newton's second law is usually our starting point for any type of question like that. I also want to remind myself this is circular motion. So I'm going to write a little c on the acceleration to remember that that's centripetal acceleration. Now, the only force acting on this satellite right here is the force of gravity. So the net force is being caused by the single force of gravity. We'll put we'll say mass of the satellite, little s for satellite right there. And then centripetal acceleration, this is where your decision comes into play, because we know a few different expressions for the centripetal acceleration. But because I'm being asked about the orbital speed, I want to pick the equation that has speed in it, v. So that would be v squared over r. It's actually on our AP equation sheet. And now I have a variable speed that I can solve for. And so this now takes just a little bit of kind of messing around with the variables. So I know this is not on the surface of the planet, right? So I'm going to use Newton's law of gravitation here to solve for this. So that's capital G. That'd be mass of the Earth times mass of the satellite, and that's all divided by the distance between them squared. And that is now equal to the mass of the satellite times the speed squared over the distance between. Okay. Remember, my goal right now, because the problem, this setup that we're talking about originally asked me about orbital speed. So I'm trying to solve for speed here. So my goal is get this v all alone. So now that's just going to take some kind of moving around of variables. One thing I noticed right away, there's both terms on either side of the equal sign have a mass of the satellite there. And so I can actually cancel those out. And when I rearrange these variables to get the speed, I end up with speed is equal to the square root of g times the mass of the Earth divided by the distance between them. Okay? That's all underneath that square root sign right there. So there's a couple really important pieces that we can figure out by looking at this, right? This tells me that the orbital speed is proportional to the square root of the mass of the planet. So I'll put E for Earth. In this case, it's Earth. It could be any planet. Whatever thing is actually pulling on the satellite or the object that's orbiting, that's what it's proportional to, right? It's also proportional to the inverse of the distance between them. So we could say that orbital speed is inversely proportional to the square root of the radius, right? The square root of that distance between them. Why does this matter? Well, what's kind of weird and a little counterintuitive is the mass of the actual satellite. You remember that canceled out. The mass of the actual satellite has nothing to do with this, which was always counterintuitive to me because I would think if this thing is heavier, you know, it's going to go slower or something. But it plays in space. That plays no role, right? The only thing that matters is how hard is this getting pulled on with a force of gravity, and that is entirely dependent on just how big the planet is, the mass of the planet, right? So orbital speed, so taking a look at this, orbital speed does not depend on the mass of the satellite or the moon or the thing that's orbiting, right? All it depends on is the mass of the planet right there. All right, so that's how we derive that equation. And then the next video that I'll have linked down below too is about what do we do if it's asking for